So what we want to figure out first is what forces are acting on each side of the ladder. To do this problem, we have to break the ladder up into two sides, the left side and the right side. So I'm going to encourage you in your drawings there to kind of just set up something over to the side where you can start drawing out all the forces that act on the left side of the ladder, and then do something similar for the right side of the ladder. Now, it's possible you will leave something out, and it's okay. We're going to come to talk together about this, but right now, all I want you to do is kind of draw in all the forces that you think are acting on each side of the ladder. And I'll take a little break while you guys are doing that. I want you to think about this. If I just put two even meter sticks together and tried to lean them together, I could probably get them to balance if I was really careful. But the moment somebody would stand on one side, the whole thing would fall apart, right? So take your arms real quick and maybe put your pencil on one side so you know where the person is. And just kind of touch the tops of your fingers together. All right? Now, for this to balance, I want you to feel that there's clearly got to be a force pushing your both sets of fingers, right? So this hand pushes to the right on this one and vice versa. You can feel that. But the one with your person, have it push down on the other hand. Feel it slip past the fingers for a minute. Do you feel that there must also be like a force up or down on one side or the other? Can you feel that? Now, the ladder doesn't hold together by friction like your fingers are doing. The ladder has a bolt that's probably right here that goes through the top to hold the two pieces together. I don't think it's too much to realize that there's probably a force this way from the other ladder, but there probably is an up or a down force too to keep it from sliding apart. You follow what I'm saying? You have to figure out what direction that force acts on each ladder. And a lot of Newton's third law forces going on here too. So think on that for just a minute and see if you can figure out where that force would be. And I'm going to start filling in some things in my diagram and compare them to yours. This is what I have so far. Is this kind of like what you have so far? You get all of those? So we're missing one on each. And this is the one we were just talking about. So to get this one right, the person is pushing down on the other side. So there has to be something from the other side pushing up on the left side of the ladder. This is to keep the left side of the ladder from just collapsing down. But that also means that the left side of the ladder must be pushing down on the right side of the ladder. These two forces are a Newton's third law pair. The left side pushes down on the right side, so the right side pushes up on the left side. And these two are also a Newton's third law pair because the left ladder pushes to the right on the right ladder, and the right ladder pushes to the left on the left ladder. So we also have one final Newton's third law pair, these two tensions. form our last third law pair. It's a single bar that connects the two, so the tension within the bar has to be uniform. We are assuming that the bar is really light compared to the ladder, so we're not dealing with the weight of the bar. I think that's fair. So now we've got all those set up. There's a lot to deal with here. I hope you realize that. We have net force in the x direction on this ladder and net force in the y direction on this ladder. We also have net force in the x direction on this ladder and net force in the y direction on this ladder. But if you look carefully at our pictures, do you realize that all of the forces are either all in the x direction or all in the y direction? There's none at an angle if this is our x and y. So take a minute on each side and come up with the force equation for each ladder. All right, let's see if we have the same things. I have on this one, nx just equals tension. There's only the two, and this side's the same, tension equals nx. Doesn't tell us very much, but okay. On this side, I have n1 up minus 50 minus 600 plus ny equals 0. Do you guys have something similar? Now, the other one's simpler because I've got n2 upwards, and then I've got 50 downwards and ny downwards, and that equals 0. Now, there's no easy way to say this. We clearly can't solve it with what we have here. We've got several unknowns, and although we seem to have a lot of equations, 2 of them are the same, so they don't really count as separate equations. I count 4 unknowns and 3 equations. So like all of these problems, net force isn't enough. Net torque is what's really going to help us solve the question. And we're going to have to go look at the torques on these. Now that's going to be tougher because there's a lot of torques on each of these. You do see that, right? This is going to generate a couple of torque equations. And I'm thinking we're probably looking at a lot of substitutions in our future here. So I don't know that we can easily, on a single page, write all of these things down. But you guys should have some things written down there now. I would say that if we want to solve this problem, we need to pick a pivot point, something that's going to be useful, something that might help us. And I'm not exactly sure where you think the pivot point should be placed, but I don't know that we gain anything by putting it in one place versus another. For example, we could put the pivot point here. That eliminates N1, and we do it on the other side, we'll eliminate N2. That still leaves us with lots of forces. If we put it here, that eliminates NX and NY, but we know that N1 is related to NY. I'm not sure that that's going to solve the problem either. But if we do put it there, it'll give us one equation with 1, 2 unknowns, and this one would give us one equation with 1, 2 unknowns. But we don't know what the tension is either. So I'm not sure that putting the pivot at the top is the way to go. So what I'm going to encourage us to do is put the pivots at the bottom. This should allow us to get what NX and NY are. And if we have NX and NY, we can figure everything else out. So before you launch into drawing your torque equation or putting together your torque equation, let's remember what all these angles have to be. it's 40 degrees between the ladder, which makes these angles 20 degrees. Those are all 20. And anyone that's not 20 is going to be the complement of 20, 70. So again, I'm going to stop talking. I'm going to let you guys put together your torque equation, but I'm going to shrink this even smaller to make room. Maybe I'll just go to another page to make room. That sounds like a fight to me. It's a lot of different torques, isn't it? All right, so these are the torques you're laying out. Kind of tried to list them on both sides. My big head's in the way, so I'm just going to be done with it. So I'm going to start at the top and just go through each of the torques. And I hope you guys are kind of following along. But how are we doing so far? I'm trying to use our same procedures. I'm going to start with the 50 Newton torque. It acts at the middle. So that's torque arm of 1, force of 50, sine 20 degrees. I made that negative because it's causing a torque in this direction. So any torque in that direction, I made negative. The next one is the person. They are 1.5 meters away at 600 newtons, and they are also sine of 20. Good so far? We don't know what the tension is between the two, but I know that it occurs at the middle as well. It's also sine of 20. And then let's see. Now I've got nx. That's all the way at the end of the ladder. So that's 2 nx. That's sine of 70. That's the complementary angle. And then lastly, I've got ny, which is 2 ny, and it's sine of 20. Well, that's a lot. So much. But this is a number. This is a number. We can get the number parts out. And I'm going to give you a bit of piece of advice, something that can help with this a little bit. You know that sine of 70 is cosine of 20. Do you know that? You didn't know that? Wow, okay. Well, you do now. The sine of one angle is the cosine of the complement. Skylar, go ahead.
Sorry, can you just explain why the tension is sine of 20 and not sine of 70?
Oh, I'm sorry. It should be 70.
Okay.
Thank you. The reason I was bringing it up is you could get rid of some of these sines and cosines, or sines and sines, I guess. If you know that sine of 70 is cosine of 20, then if you divided everything by the cosine of 20, it would effectively remove the trig function from some of these. Because some of you don't like that there's trig functions in here. Or you can consider that the sine of 70 and the cosine of 20 are just numbers, and you can just compute those real quick and put them into the problem. Either way, we've got a lot of unknowns that we still have to deal with. So if I were you, real quick, I'd put these together and get your equation and set it equal to 0. It's a lot. I know. So what is the sine of 20 degrees? Can somebody just give me a couple of digits? And what is the sine of 70? Thank you. Whew, that's a lot, isn't it? So many things. This is too many calculator buttons to push.
I think the second value is supposed to be 307.8.
Okay, I'll fix it in just a minute. But thank you for catching it. So I was off by a decimal. 307.8.
Yeah, 307.8.
Right. Does yours look like this though? Everywhere else? Check
Yeah,
my
seems
work,
to be.
because yep, because it's two away, right? Thank you. Wow, 2 mistakes in one day. Might as well quit and go home. All right, so that's one of them. However, we can make it a little simpler. T equals nx. So we can either sub in for t or sub in for nx. Doesn't really matter. It's not going to make it that much easier, but it will get rid of one of the unknowns there. I would get rid of the t. But it doesn't really matter because nx and t are equal. Now we have to do this all over again for the other side. Sheesh. It's a lot. So I'm gonna let you guys do that. I'm gonna clean this one up while you guys are doing that. So much work. What is going on out there? They're having a great lunch, aren't they?
It's 324.9 at the beginning.
324.9.
I second
Yeah.
that.
Yay. So the other side's got a lot of stuff going on too, doesn't it? But we're going to see that there's some stuff that just cancels out. We just got to get there. And finally, are all those the things you guys got for the torques? Now, I don't know if you see this, but we have the same combination of torques on this one as we did over here. So they're going to cancel out between the two relationships and leave us with just NY. Meaning we're going to be able to solve the problem for NY right here, right after we get this next relationship. We just have to get all the stuff down. And all of it's, we've already written all the same numbers. The only difference is there's not going to be this number here. And this one's going to have a different sign. So we've already done all the multiplication you need to do. So we're going to put it all together, but 2 times the sine of 70 times nx, you already know that's going to be, I'm running out of places to write. So I'm going to write it right above it. It's going to be 1.878 nx. And my 2 times ny times the sine of 20 is going to be, what, 0.684 ny. And the t sine 20 is going to be 0.9, nope. T sine 70, so it's 0.939 t. And then I've got my 50 sine 20, which is my 17.1. So it's positive on this one, positive here, and it's negative here, and positive there, and that all equals 0. It's a mess, I know. So are we all to this point together? There. So I just want to bring all these pieces together so we can kind of look at them together. If you look, because they all equal 0, we can go through and realize that we can get rid of some stuff here, right? We placed the t again with nx, just like we did before. Add those two together, and we're going to get negative 0.939 nx. And we got the 17.1 here and the 324.9 here. They're going to add together to be just this 600, what we had before. So if we add these two things together, that goes away. I get 2 times 0.684. I don't know what that is. What is 2 times 0.684? So 1.368 ny equals negative 324 plus 17.1. Isn't it 300 and something? There it is, finally. Boy, that was a lot of work. So much work. The ladder problem is just brutal. But if we had just done the torque first, we would have been able to solve for ny almost immediately and gotten it by itself. Everything else here has been garnish. So, oh, you're all getting nervous. We can get rid of, well, I moved it to the other side of the equal sign. So we can get rid of all of this work and realize now that we have ny, we can figure out the whole problem. So what is ny? Somebody do the little division for me so we can get a value here. 200 and what? 225 newtons. Now look at all the places that we can use that. Ny is 225 newtons, which means right here, we can figure out what N1 is. And right here, we can figure out what N2 is. Not so bad. So N1 is going to be 650 minus Ny. And N2 is going to be 50 minus or plus Ny. I can't do that math in my head, but I know you guys can. Somebody give me N1 and N2.
N1 is 425 and N2 is 270.
Adds up to be 700. So we must have done something right. N1 has got more of the force than N2. So I feel confident in that. And I know that that was a lot of work. I wanted to go through the whole thing for you with you so that you could kind of see what these kinds of problems look like. And I know that you're thinking, this is way beyond what would ever be on a test. Because just how long did it take? I mean, we spent the entire class period on it. And that assumes that you know exactly what to do and where to begin. We're not cutting any corners here. But I do want to point out that imagine what it must be like to build like a bridge. I mean, a bridge doesn't look all that impressive until you realize that all those other things that go along with it. Consider like, you know, a bridge that has some kind of structure involved. You know, like maybe it's got these kind of cross members in here. Could you imagine all of the work that has to go into figuring out how the forces are dissipated through a bridge like this? Now, computers handle most of the work now. But this is a process of constantly looking at the net torque and the net force acting across the whole object. We only had two things interacting, two beams leaning on each other. And this is what it took to get that work done. And we haven't really answered the whole question, have we? How do we get the tension here? You actually have the answer in front of you. You've got two torque equations now where you know the answer to Ny. Either one of them, you could plug that value back in and go get the tension. So it's not hard to figure out what the tension is. We've kind of exhausted every possible point of this problem. Now, I wanted you to see this because I think it's a good experience. I don't want you to be scared of it because I don't want you to feel like, wow, that's going to be on the test. I want you to understand, though, that just standing on a ladder, just the guy who designed that ladder at some point or another had to do all of this, probably mostly to figure out how big a bolt do I have to use here at the top to hold the two parts of the ladder together. If I don't use one that can sustain enough of this force, the ladder falls apart. How much force is it? Well, we know now it's this much force. And that's if he stands close to the top. Now, if you've ever been on a ladder, you know at the very top it says, don't stand on this step. Part of that is to protect the ladder. Part of it's to protect you. Now, I just want you to know we are making a colossal mistake. And because I want you to have an understanding of physics, let me make sure that you understand what the mistake is. The person's weight is not concentrated here. There's actually a torque arm to the person's center of mass there. This is how you fall off a ladder. This isn't about the ladder anymore, but this is how you fall off a ladder. Anybody who's ever climbed a ladder realizes that if you're not careful, you can fall off of it. Anybody ever get on a ladder and feel like they're going to tip backwards off the ladder? This is the torque that causes this. The more your center of mass gets close to that edge, the more likely you are to tip backwards and perhaps bring the whole ladder down with you. You tend to not be able to climb straight up a ladder. Have you ever watched somebody climb up a ladder? They feel a tendency to lean forwards. It's because of this instinct you feel in your feet to keep your center of mass over where you're going. And that actually saves you by encouraging your center of mass to be more over the ladder and less behind the ladder. Coming down the ladder, though, you tend to lean backwards, which works against you, you understand. So when you're coming down off a ladder, you should keep your hands on it. Because if you don't, you could lean too far back and bring the ladder backwards, because the moment this comes over the top of that foot, you're coming off the ladder. Whether you want to or not, the ladder's tipping with you. So if you understood how to do the bridge question from yesterday, that's really the extent to what you need to understand for statics problems in this class. So if you can figure out a person walking across a bridge and how the force is distributed, that one-dimensional problem, you're going to be fine. If you could follow this argument, but maybe couldn't replicate it, that's okay. I think it's a good experience for us to see, but I don't necessarily think it's something that you have to be able to do. But this is going to end our discussion of statics. The likelihood of a statics question is about 1 in 7. They don't ask it very often. If they do ask it, it tends to be on the multiple choice. So that tells you the level of depth they're expecting for statics. Dynamics, on the other hand, is what we begin next week. I've put together a homework assignment for dynamics. It's going to be due next Friday. I think we're going to finish the first part of dynamics probably by the end of next week. So we're probably looking at a test that first week of February. Any questions about that? All right. Enjoy your lunch today. You guys at home have any questions about that?
I have one question.
Okay.
So would they have